Good. Okay, so today what we're going to do is we're going to continue our look at change, right? Which, remember, change, gradient, slope, the letter M, all of those mean exactly the same thing. Right? Okay? They all mean exactly the same thing. And remember that anytime you see one of those, think derivative. Yeah? You find the slope or the rate of change by finding the derivative, because what we're doing is finding the slope of the tangent line at a given point, right? So, now, today we're gonna focus on rates of change. So we're gonna shake it up a little bit in that we're not just gonna have functions that are in x or just f of y. We're gonna have actual functions that do things. In other words, functions that describe things. So the letters will change. Do you think that'll change the process? Absolutely not. So if you have time and distance, they'll use t and d, right? Yeah. So it's no big deal. It's just that they're being very specific about the variables that they use to make it match the situation. So don't let that freak you out a little bit. Also, there are going to be some units here because we're going to be talking about applications using real things. So you will have some units that you need to be aware of, okay, for these applications of rates of change. So rates of change, we're just talking about how fast something changes given a certain set of circumstances. And we're going to look at three different types of rates of change. And so you need to know what to use. So what to do is determined by what you know. Imagine that. Doesn't it? Okay. There you go. Now, so if you know x, now it might not be x, but x is usually the variable in a function, right? F of x equals blah, 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 x squared plus 3x minus 2. That's what I mean by knowing x. It could be t, it could be whatever, but it's the thing, it's your independent variable. Right? It's the thing that drives what's happening. Okay? You could also know your y. Okay? So in other words, that's the f of x part. So that's not on the... So generally we have something like this. F of x equals x squared plus 2x minus 4, something like that. If you know your x, that means you know the thing that's on this side. Right? If you know your y, that means you know that piece, because f of x is the same thing as y, right? Okay. Or you may know the gradient, or change, or slope, or whatever. Gradient's the word we've been using, but now they're going to change it and use rate of change instead. But it means the same thing. If you know that, remember that's the same as saying that's your derivative part. F prime of x. Okay. So what we're going to do is we're just going to be substituting. Some of them we have to find the derivative first. Most of them we will, actually. You're going to find the derivative first, and then you're simply going to plug in the thing that you have. If you know the value here, your independent variable, then you plug it in here, right? If you know the y is the same thing as saying your f of x business, so that'll go there. If you know the gradient, you'll plug that in place of the notation once you've done your derivative. Yeah? So it's just a matter, and we've done exactly the same thing before, but now we're doing it in relation to applications. Okay. So know what it is you're given, so you'll know where to put it. And then it's just a matter of doing the algebra, doing the math. Actually, arithmetic from then on, right? Okay, so let's take a look at some of these, and we'll just do one of each type, because I think that you'll see that they're very similar to what we've been doing. Okay, remember that The gradient tells us how fast the variable on the y-axis is changing compared to that on the x-axis. In other words, how far is it going up compared to how far it's going to the right, or how far it's going down depending on how far it went to it's on to the left, right? Now, so you may be told the value of x. That's one of the situations. You could be given the value of the gradient. You could be given the value of the f of x, the y. Any of those, but you'll still work with the same process. Remember from our look at increasing and decreasing, how do we know that the rate is increasing? The gradient is what sign? Positive. If the gradient is negative, that means the rate is what? Decreasing. So keep that in mind as you're going, because you're going to be answering questions based on that. So put some things together. So just look at this first example really quickly. If y equals x squared minus 4x minus 1, then dy dx is 2x minus 4. All they did was take the derivative, right? And we want to find the rate of change, which is the same thing as the gradient, at x equals 3. So that just means they've given us an x value. We're just going to plug it in, do the math, and find the gradient. So once they plugged that 3 in place of the x from your derivative, it gives you positive 2. That's not x equals. That's dy dx equals positive 2, right? So let's think about what that's telling us. It's a positive value. That means that it's what? Increasing. And remember that it's increasing at a certain rate, and that rate is 2 whatever units. Okay? If it could be centimeters, getting bigger, so it's increasing by 2 centimeters. Okay? It can be increasing by whatever. So now that the only thing changes that it's going to have some units. But in this case, we don't know what it is, so it's just going to be 2 units. So so the answer would be that it's increasing by 2 units. Again, you'll normally be told what the units are, so you have to put that in there. But for this one, we were given no units, so you just call it units. All right? Keep that in mind, because many times students forget to do that when they don't. If you're not given a unit, then you just call it units. All right? Okay. So as x increases by 1 unit, y increases by 2 units. Because remember that a 2 is really a 2 over 1, and that's a rise over a run.
So would that be like, if it was like this instead, it would be like meters per second?
Exactly, meters per second, or centimeters squared per centimeter, or whatever your units are. Mm-hmm. And we'll look at some that have units in there. So 2 over 1, so remember that the top number always associated with your y, the bottom number always associated with your x. If it's a whole number, so whatever this is, so that means the denominator is always going to be a 1, so it's per 1 unit. Okay, for each unit. These are always going to be per 1 unit. Okay?
How do we decide that we're going to let x equal 3?
That just told us that, where x equals 3. So that came straight from the, yeah. It was just stated in the problem. So we didn't pick one. But you could, but it's a good point, though, because they could tell you to find it on the x-axis. So that's where, like in this one, it would be right there. Or on the y-intercept, which would be right there. So you could find it in other points as well. Yes?
When it says that we know that y equals negative 4, is it just you have to like find it or something? Or is that?
Okay. Well, if x is 3, all right, so then they to find the point, that's what we did last time. Remember, we found points. If you know x is equal to a certain number, right? If x is equal to 3, then find f of 3 in your original function to find the y value. So they just went back to the original function, put in 3 everywhere there, and found the y value. So that's exactly what we did last time. So you see, everything we've done is exactly the same. The only thing that's going to be different is now you're going to be describing it as increasing and by what rate. Yeah? So the math is just the same, exactly the same. If I want x, I plug in y to get it. If I want y, I plug in x to get it. right? Same exact math that we've been doing. Okay? So let's look at one where they give us in context. Okay? Again, remember, they don't always have to give you x and y. So the surface area of a cube changes as the length of the side increases. That makes sense, right? If you increase the length of the side of a cube, then the surface area is going to also increase, right? That makes perfect sense. Well, we want to find out by how much. So that is a rate of change. Okay? So we're given the function. Area equals, forgot to push my button. Area equals 6L to the second power. Okay? So that's just the function. It's not a derivative. It's not any. I knew that because it doesn't use the dx, dy, or dA, dL in this case, but it doesn't make any difference. So find the rate of change if the surface area with respect to the length of the side when the side is 5 centimeters. So 5 centimeters is a length. Do you agree? Our formula here has area and a length. And if it says 5 centimeters, we know that's not an area. How can I tell it's not an area? Because it's not square units. Right? So you can be able to tell which one's which. So that means that all I need to do to find that, so to find the area, is first take the derivative of the function. So you see that they did that. 2 times 6 gave them the 12. 2 minus 1 just made plain old L. And dA, dL. Don't put dy, dx.
What if we did?
That's a sad mistake to make. The derivative of x derivative of y in respect to x, derivative of x. Remember that?
Okay.
That's that notation, and that's where the d comes from. All right, I'm thinking yes. If it was, this is going to be an external markers, and I don't know if they're told specifically to ignore it, they will. But I'm telling you that I got whacked in calculus way back a million years ago for it. Improper notation, if you say something is equal to something that it's not, that's a bad thing. Okay? So that's why they're putting DADL.
Can you use the brackets? Can you go A and then bracket L?
Remember we discussed that. I wouldn't. Pardon?
So you use that.
Yeah. If it gives you just a letter like this, now, if they said F of L, that's when you'd use that notation, right? F of whatever. But so use the 2 different notations. Remember, that's the one I did check on for y'all, and they said, and Ms. Brader said, use the proper notation. So, okay? And yeah, it's going to be a pain, but you'll get used to it because you'll do a lot of these. Okay? This is one of the main reasons we use calculus. All right. So differentiation, the function. So you see that they've taken the derivative. We're just to then substitute the 5 in place of the L because that's the length we're looking for. And then it gives me 60. So that means that the surface area, it's positive, so it's increasing. So look at the way they write the answer. When the side of the cube is 5 centimeters, right? We said that the surface area is increasing. We got that because our slope is positive, our gradient is positive. At a rate of 60 centimeters squared, because remember, all right, per centimeter.
Yeah.
So, because it's surface area it's area we're talking about, so that's why it's squared per centimeter. Now, in reality, what would happen if you did that? 60 centimeters squared per centimeter is really just, yeah. But don't do that part. Don't simplify it out. But I just wanted to mention it because some of you are going to want to build that as a fraction and then notice that the units would divide away. But talk about it in context with using words. Okay? All right? So you see that the math is exactly the same as we did last 2 classes. It's just now we're having some units and we have to describe what is happening. Okay? Remember from your last experience with NCEA, they are very, very particular about the way you describe things. Right? Okay? So make sure that you're particular about the way you describe things as well. Okay? Now that was one where we knew the L, which is like knowing your X. Right? Well, you could also have some, so you're going to have some where you know that. There we go. Look at all those. Don't you love it? And then you're also going to have some where you're given the Y value. But remember, these are going to be given in context using other letters. So in other words, where it would say f of x, it's going to give you different letters. For example, this one, h of t, t is time, and h is a height. Okay? So you have h of time, the height of time. Okay? So, but it still means the same thing as f of x, which is the same as saying y, right? It's what you get if you put a value into the x and work it out. Yeah? So to find y, I solve the equation for x. So let's look at what that looks like. Again, it's just a matter of where you're going to put your number. Do you put it in place of the t? Do you put it in place of the h of x? Do you put it in place of the slope? And in this case, an object is dropped from a height of 200 meters above the ground. Its height m above the ground after t seconds is given by that function. Now, so do I know the height or do I know the time? Height. So I can't put in a t, I'm going to put in the place for the h, right? And even though it's h of t, that's where I'm going to put it, right? Just like you'd put your y. So we simply put in 200 meters. Okay, I'm sorry, that's the original function. Find the rate of change when the height with respect to time when the object is 110 meters above the ground. I'm sorry, I forgot to do the change part. Okay, so 110 is our h of t, and notice the function didn't change because I don't know t. Okay? Then we simply solve to find our t. Because I remember when you're plugging numbers into the derivative, I can't plug in my y. I have to always plug in an x value, right? So I need to solve for t. Okay. So first, substitute the f of x. Second, solve for x. Now, I'm using those same general terms that we did before with the x and the h of f of x. But in this case, it's t, really. Okay? Then, differentiate. Then, find the gradient or rate of change. Same difference. So I'm just showing you that the math is not any different. The directions are the exact same ones we've always used. Okay? So, let's look at what they did. They plugged in the 110. The function stayed the same. They got their numbers on one side. So it was 110 equals 200 minus 10t squared. So they moved the 110 over here by subtracting it from both sides. Gives you 0 equals 90 minus 10t squared. Then they moved the 10t squared away from the 90. And the reason they did that was because by moving it a negative, you move it by adding. And so that turned it into a positive. Now, you do not have to show all of this solving. I just want to go back and remind you what's happening here. And then you simply divide both sides by 10 to get that t squared by itself, which gives you t squared equals 9. Then I'm going to unsquare it. How do you unsquare it? Square root, yeah. So I get t equals plus and what? Minus 3.
But since you have negative, so you can
there you go, right? T stands for time. Time can never be negative, so we reject the negative. That's an excellent part right there. If you'll make a little note saying that, yeah, it shows understanding. So even if you make a tiny error somewhere else, if you show that little bit of understanding there, then someone can infer that you do have a deeper knowledge. Okay? So don't forget, any place you can, that doesn't mean write a book, but any place you can say something like that, then you could. So time can never be negative, so we're only going to use the 3. Everybody see that so far? Okay? So, oops. Okay. Now, then they simply found the derivative of the function. Guys? Okay.
Like if you started like,
It's a man-made concept.
well, yeah, that's the point. That's it was
Anyway,
physics, right?
Existential discussions aside. Okay. So then they found the derivative of the function, plugged in that t value, and then were able to find the rate of change. Now, we just said that 3 couldn't be negative because time can't be negative, but when we plug in that information, we end up with a negative number. Can that be possible? Yes, because it's meters per second. It's rate of change, and rate of change can be negative. That simply means it's decreasing at that point. So it's decreasing at a rate of so many meters per second. So the height of -10 after 3 seconds, the object height is decreasing. Yeah, if you didn't get decreasing on this, then there was an issue.
No, it means it's a helium balloon.
At 60 meters per second.
Wait, so...
Okay?
Speed's not only decreasing.
So if you don't know the thing that's on the independent variable, you have to find it first, and then go right back into what we were doing. Okay?
So, like, okay, and then you do...
And then we did exactly what we did before.
Okay.
Okay?
Okay.
All right. In order to make this work, I have to know what t is.
Okay, yeah, I get it.
In other words, so no matter what else happens, I have to know what t is to make this work.
Okay.
Does that make sense?
Yeah.
And so they didn't give me t, so I had to solve for t
I was
first.
wondering where the 110, but then I
Yeah.
realized that we wanted to here, so we didn't need it.
Yeah, we don't need it anymore. Okay? All right? Now, the only other one is what happens where they give you the rate of change and they want to know the other pieces of information. So let's look at those. Right? So we're going to be given the dy dx, in other words, the rate of change, and we need to find our x and y, was what we normally call it. Okay? For example, a vase is left under a dripping tap. The height of the water in the vase after t hours is given by the equation. So this is already a rate of change, right? The height after t hours. Okay? So here's our function, okay? When find the rate of change in the height with respect to time is 2.1 centimeters per hour. So here we go. So 2.1 centimeters per hour. That is, if that doesn't scream rate to you, then you need to make sure you know what a rate means, right? Miles per hour, centimeters per hour, feet per second, whatever. That's a rate. Per is your clue, always.
Wait, what is it asking for?
Okay, well, hold on a minute. Let's find out. Okay? So, find the rate of change in the height with respect to time. Okay, I'm sorry. It says when that we need to find the height and the time. We know how much it's changing, but we don't know the height and we don't know the time. So that's what we're going to be looking for.
And so when the rate of change is 2.1.
And so the rate of change is 2.1 centimeters per hour. So rate of change is, we are going to put that in place of that in the derivative of the function. Because rate of change is a derivative, right? The gradient. So let me clear my marks here so that we can see what's going on. You've done this one before, okay? It's just, again, it's a matter of what do you know. So we know the rate of change, and we know that the rate of change is the derivative of the function, right? That's this bit, is the rate of change. So in place of that bit, I'm simply going to put my 2.1. Now, why they always reverse these, guys, why they always reverse these, I know you're talking about math, but you're doing it too loudly. Okay? So in place of that, I'm going to put 2.1 and the rest of the derivative. So first, take the derivative, step 1. Step 2, solve it when you replace that with the rate of change. So that's what they're doing here. So 2 times 0.2 gives you 0.4 t, and then t times is t to the first. So 1 times 0.5 gave you 0.5, and the derivative of t is 1, which you don't need. So we just replace that number. And for some reason, every time they do that, they always reverse it. And that's why I just rewrote it, so you can see that those two things are the same thing. Right? Here's the way they write it when it's a derivative, but when they put the number in, they always seem to put it on the right-hand side. Don't let that confuse you. Doesn't matter which side you put it on. I always put it on this side because that's what I'm replacing. But you do what you want. Doesn't make the slightest bit of difference to solving it. To solve it, get all your numbers on one side and your t's on the other. So we'll subtract the 0.5 from both sides. Right? Which gives us what? 1 point... Somebody want to do the math for me? 1.6
1.6, yeah.
equals 0.4t.
Which is 4.
And then we'll divide both sides by 0.4 to get the t by itself, which gives us 4. Right? Okay? So we got positive 4 as our t. So that's our time. And our time is given in hours. So it's 4 hours. It took 4 hours for the water to reach this level, right? It's a very slow dripping tap. Okay? Now I need to find the height. How do I find the height? Well, if I know t, I plug it back into the original function to find the height. But they didn't even ask you for the height. They were just asking you if the height of the water is increasing at 2.1 centimeters per hour after 4 hours.
Next time I leave my vase under a tap, I'll do this.
Yeah, you better do the math. Because I am always leaving my vase under a tap and leaving it dripping. Yeah.
That's very
Leave and I forget about it, and I'm wondering.
I didn't say the questions had any relevance to anything for anybody, just that there's context. Okay? The context may be stupid, but it's still context. Okay? So do you see that you're doing the same math? Don't get freaked out by the fact that they're talking about rate of change. Okay? All right, let's